every time I come to this little part of the world, it's like sunny, beautiful weather. I don't believe it actually ever rains here. You say that, that's just to kind of keep people away, I think. Anyway, it's a beautiful center. As I'm glad I had a chance to tour it. I've been wanting to see it for a long time. So today, this afternoon, we'll take a slight change of directions. Talk about, first of all, hardware. And even the hardware I'm going to talk about, I sort of selected a subset. I'm not going to talk so much about high field, although I'll show some high field results, and really talk about the ancillary hardware, which people tend to forget about, but really makes high field come into its own. To get that beautiful laminar structure, you really need that high-res EPI. That means, of course, good gradients, but also good RF receive coils for accelerated imaging. I also threw this picture up on my slide because it's the one thing I'm also not going to talk about, which is our Connectome gradient set. Camille talked about his a little bit. We have a big gradient, and it's wonderful for high B-value diffusion, but that's a source of a different talk. Before I get too far along, I just want to acknowledge my group. I never have time at the end, especially John Palomini, Cowan Setzenpop, Boris Kiel, Thomas Witzel. You'll see a lot of their work, actually everybody from the whole group. So the sort of premise of my talk is that you can get these beautiful 7T images. This is a standard T2 star weighted image, showing, in this case, we were really trying to get down the brainstem and pons, that it's really RF is everything in these images. And it's going to just get more important. Whoops, misspelled getting more important. And the brain doesn't end at the tentorium, that there's more to the brain than the cortex. And one of the focuses that we want to do is, kind of get down to this area and below in the brain at 7T with the same sort of exquisite sensitivity and the resolution that you saw in the cortex. And one of the first things your 32-channel coil can do at 7T that wasn't available a few years ago was what Camille mentioned with the simultaneous multi-slice. This can, of course, be combined, applied to standard imaging as well as EPI. It's actually much easier in standard imaging. And we can take this high-res image, which we only got 11 slices because they're cardiac gated, and just with a simple throw on a switch, we get the same quality images, almost identical. You can't really tell the difference, except we got 3 times as many of them. Now we can cover more territory per unit time. And so that's kind of a no-brainer. There's really no cost to that. Of course, the RF has really allowed us to do this. When we started with EPI at 7T, we were using 8-channel coils. We really got noticeably poorer EPI quality than at 3T. And at 3T, the EPI is not particularly beautiful. This is a classic 3mm isotropic. And it's really, I think, thanks to the coils and the generation of gradient coils we have, that we can now get this sort of super EPI that I like to think of it as, like this 0.75, which we've seen. And this is now being routinely done around the world. And I just want to take a minute to point out that you can see plenty of anatomy in this image. It's 0.75 nominal resolution, but the resolution is really there. You can see the cortex, you can see small vessels, you can see everything. The only downside is a little bit of distortion, because in this case it's R=4 acceleration. It's not quite perfect. Here's just to zoom in on that a little bit. And so one of the things, well, the next step is, of course, when you have this high resolution, you can't cover the brain. As Camille mentioned, the solution for that is simultaneous multi-slice. It really, I think, in our hands, being able to turn on the blips really made this method work. We invite you to try it without the blips. It's a remarkably different world. And this really just changes things. And suddenly you have, like Camille mentioned, these ultra short TRs, in this case whole brain, and 350 milliseconds, 2.5 millimeter resolution. We've been working hard on the reconstruction, so we can reconstruct 170 slices per second in real time without dragging behind. And this is the work of Cowan and Steve Cowley in our lab. And this has really changed things. And a lot of people will say, well, who cares? You know, don't you know the hemodynamic response function is only 6 seconds wide? Is 6 seconds wide? Why do you need to oversample it? You're just oversampling. And there's actually a really nice way to think why that thinking is actually wrong. That when we sample with MR, when you sample properly, like that thinking comes from, of course, sampling theory, which is perfectly true, that if you oversample and then you sample at a higher bandwidth and then you low-pass filter down, you just get the same result as if you just sampled slower with a lower bandwidth. But that assumes that the sampling period, where the ADC, sample and hold, is actually connecting a capacitor to the voltage that you're measuring. That sample and hold is down for 1 over the bandwidth. And so that's the way ADCs are designed. And when they're designed that way, it's perfectly true there's no point in oversampling and then a low-pass filtering. But with echoplanar imaging, we're sampling the signal only for 30 milliseconds or so for the EPI readout, maybe 50 milliseconds in these higher resolution images. So until your TR is 50 milliseconds, there's large periods of signal that are going unsampled and unintegrated on the equivalent of a sample and hold. And when that happens, it's simply inefficient sampling, and you're not integrating the noise out. So you do get an actual benefit from this oversampling in EPI. The other thing that struck us is now that we have these EPI that quite frankly have higher spatial resolution than our standard images, why are we doing standard images anymore, right? I mean, the EPI is very fast, wickedly efficient, and it's actually quite nice to have all of the images have exactly the same geometric distortion. And that's easily arranged with an all EPI acquisition, because you can, for instance, take T1 EPIs. In this case, we took our standard 1.1 millimeter isotropic resolution. We did 24 TI preps, so 24 inversion times, got the full range of T1 weighting, and we fit a T1 map. And the nice thing is this T1 map is very general. We can use it to generate any different T1 contrast you like. So if you like gray matter null, no problem, generate that. If you like white matter null T1s, generate that. You know, what is something in between that shows the anatomy slightly better? Fine, just synthesize those images based on this T1 proton density map that you've just taken. And it takes, 4 minutes, so it's even a little bit faster than the standard MP rage or MP2 rage. And most importantly, it has exactly the same distortions as your functional imaging will have, so your data is in complete alignment when you superimpose it. And we simply synthesized the T1 weighting that FreeSurfer happens to like, which was based on basically a 1.5T scanner many years ago. And we run the EPI through FreeSurfer and generate the surfaces now. And then we can rest a little easier at night knowing that those laminar surfaces are exactly distortion matched to the functional data. There's no sense stopping at T1. You can take an EPI that's T2 weighted. That's simple, just make it a spin echo. Again, the same exact readout, so the distortions are the same. And you can, of course, get T2 star. That's basically what the functional images are. And you can do diffusion imaging, which we find actually quite helpful for our brainstem work, that the diffusion contrast is really helpful for figuring out where you are in this complex anatomy. Maybe if you're an excellent neuroanatomist, you do a little better than me, but it's really nice to have a few extra landmarks down here. So I want to move on to the next sort of step that we see beyond the simultaneous multi-slice, and it's something we call wave caipirinha. It's something that could be applied to 2D imaging, but it's perhaps best applied to 3D imaging. And it works like this. This is a standard flash acquisition parameters. You have readout lines along KX. Those are the readout lines. They're nicely geometrically sampling a grid. If you undersample this, say with 3x3 acceleration in each of the 3 times in each phase encode direction, you get something like this. And the standard Kuiperenia from Würzburg simply shifts one of the lines and does what I'd like to introduce as a Quincux sampling scheme. This sampling pattern actually has a name in the signal processing theory, and actually it's a 2,000-year-old word, so we might as well use it. It's called the Quincux pattern. And our idea is to keep this pattern. It's very nice because it throws the aliases into the corners of the images, but we simply add to it a corkscrew-like trajectory. So instead of doing lines in kx, we turn on sinusoidal y and z gradients to take a corkscrew pattern. And this throws the aliasing everywhere, as you'll see. So this Quincux pattern is the 5 of the dice, that's standard Kuiperenia, and that's named after a 2,000-year-old Roman pattern that was used in a coin. And some people will call it a hexagonal pattern. A hexagonal pattern is sort of a special case. You can do the math. They're not quite the same. They're very close. In any case, the idea with the wave is you simply throw the aliasing pattern everywhere. The more you can spread out the aliasing, the better, as far as I'm concerned. Now you can use coil distributions in 3 directions to try to reconstruct the image. And the nice thing is that the shadow of the trajectory is simply going in a circle. Circles are done with sine waves. Sine waves are the basis set of Fourier encoding. So when you try to reconstruct this horrific-looking encoding matrix, you find that preconditioning it with a discrete Fourier transform matrix just makes it vanish into a sparse matrix, and it reconstructs in a quarter of a second. So it's no problem at all. So that's the real beauty of it. And it really drops the G factors, as you can see here. That's the idea behind all these aliasing tricks. I don't even show the standard one, which has quite high G factors, at least twice this. Then bunch phase encoding, and then you can see you get the G factor down to essentially nothing, so you're just left with the square root of R penalty. And we've been applying this, in this case, to standard phase imaging and susceptibility mapping. This is a tissue phase, this is a susceptibility, and this is a 2.3 minute acquisition at 7T, 1 millimeter isotropic. So we can really go fast and get good quality images with this method. So what's at the end of the road? What do we need? More channels? That's 32 channels. I would argue that we're dying to have more, that 7T will really shine once we get above 64 channels. 32 is kind of marginal. Sensitivity, extended coverage beyond the tentorium we need, and we need B1, B0 shimming through the RF coil, and I'll explain that in a minute. Here's a RF coil we made for our 3T scanner where we actually have the channels to plug it into. We built a matched 32 and 64 channel coil on the same former, work of Boris Kiel. Here's the coils. And for unaccelerated imaging, it's kind of unimpressive. The 64 channel does a little better, especially in the outer parts of the cortex, but nothing so much that you'd rush out and build one. But for 4-fold accelerated imaging, which is the minimum where we want to be at 7T, I'd argue we want to be 4 times 3 or 4 in plane and 6 multiband factor. We really want to be much higher than this. This is where these higher coils excel, and there, even in the center, which is a hard place to beat, we do a nice factor 25% better, and that's because all the aliasing, the G factors pile up in the center, and this coil simply has a better G factor. So the 64-channel brain array at 3T has been the nicest coil we've made. This is a 3.5 minute, 1 millimeter MP range, and modeling just shows it gets better as you go to higher field. At 7T, the smaller elements are more fully body loaded. This is a measure of unloaded to loaded Q, showing that 64 channels is just about the limit at 3T. But at 7T, we can go all the way up to 128 channels. Here's a simulation of 128 channels at 7T, showing that same effect. Nice improvement in the outside, but a significant one in the center too, 36% higher. 36%, that's like going from a 7T to a 9.4. So we want to extend the coverage. I mean, beyond the tentorium, this is a sort of territory where the sea monsters exist. And people have, like me, have been afraid to scan down there at 7T because of all of the known problems. And so we wanted to take a kind of sober look at that and see whether these old maps really were the truth anymore. Because you look at an image like this and you think, well, that's not so bad. You know, it's pretty artifact-free. True, it's a cardiac-gated image, took a little longer. But you look at the phase map and you see where some of the problems might come from. That it's a pretty horrendous shimming environment as soon as you get below the thalamus. And above the thalamus, it's quite fine. So we're going to need some improved shim technology to make images down here that look as good as up here. The next thing, you look at the old articles showing the movement with the cardiac cycle. You know, the idea is that somebody's tugging on the spinal cord and like a bell cord and pulling the whole bottom of the brain down by millimeters. This is a cardiac gated cine, fairly high resolution, as you can see flash. I think it's like 1/3 of a millimeter pixel in plane. So it's looping through the cardiac cycle. And I put a few pointers so you can kind of get a reference. And it's funny, if you stare at this image for about 5 minutes, you appreciate that there's waves of intensity variation going through it. And there's waves of kind of spatially modulated intensity variation, but there's very little motion. We simply don't see that 1-2 millimeters of motion that these earlier papers showed. And I think that those waves of modulation are likely due to breathing and other aspects. And of course, you see the swirling CSF that just goes crazy all around. And you could imagine subsampling this at 3 millimeters, you would get crazy partial volume changes that would perhaps fool you into thinking it was motion. And if nothing else, you clearly see that you have to avoid the CSF. The CSF is the enemy down here. It's got huge variations. If you're doing resting state, it'll drive, phony correlations. It's just bad news. So I think some of these sea monsters are really kind of petite. They're not as bad as we feared. And we can probably travel down here without being eaten, unless we're a fly. So we started building some coils. These are 3T coils again. This is our 64-channel head neck coil. And frankly, this is the sort of thing we'd start at 7T, maybe at 128 channels. And it does a nice job at improving things in the C-spine and brainstem. I mean, these head coils, like the Nova Medical coil, like the one we use, they're simply not designed to work much below the tentorium. Of course, diffusion tractography is also another reason to go further down. Here's a commercial version of our coil that's now released by Siemens at 3T. And we went on to make a C-spine coil for 7T. This is a 19-channel receive array just for the C-spine. You can see it's sort of anatomically shaped. And sure enough, the T2 star-weighted images, high resolution, about the same as we get in the brain. They're just beautiful. This is a case of a spinal cord injury, which I guess is not so beautiful, showing various sorts of pathology like filarial degeneration, hemosiderin accumulation. This is a case of an ALS patient where the cortical spinal tract is just got a bit of inflammation that shows up bright on this T2 star that's just exactly a textbook match to where the cortical spinal tract should be. We went on down to see if we could see some functional imaging, not quite in the brainstem, but in this case in the PAG, periaqueductal gray. Here again, we need resolution. This is 3 millimeters, a lot of CSF partial voluming. That's a single shot EPI through the cerebral aqueduct, which is this little bright thing right there. The PAG is around it, can't really see anything. 1.5 millimeters, okay, now we're starting to see, we can see the PAG. The fact that it looks square might be a little disconcerting. This is 0.75 millimeters, and now we can actually kind of see the anatomy down there. So that's a single shot EPI, and so we're sort of in business for trying to do activation in that gray matter. And sure enough, with our collaborators, Lisa Feldman-Barrett, who's showing emotionally adverse images, we're able to see activation in not only in the PAG, but in various locations and quadrants around the PAG, which has implications for this sort of processing. So we kept going down the brainstem. This is an ICA analysis shown with some diffusion data, and in this case, it's a masked ICA. Again, the CSF is a culprit, so you have to leave it out and make sure you're blocking it so it's not driving in ICA analysis. In this case, we get about 70 robust locuses of resting state activation in the brainstem. And some people say 70, that's way too many. It's actually right about what the ICA analysis predicts should be right. And in the brainstem, there's 500 down there. There's no shortage. So it's not a crazy number. Here's 12 individual subjects showing the VTA in each of the 12, absolutely reproducible in individuals. And the only one that didn't show it was number 6. Have no idea what went wrong there. But again, this is the promise of 7T, is that you've got robust activation, not just in a group of 30. This collaborator, Florian Biesner, just got done doing a similar analysis at 3T. He used 30 some odd subjects. We immediately saw this activation in a single subject. That's really, in one sentence, the dream of 7T. Once you see the resting state patterns in the brainstem, you of course want to know where they connect in the cortex, so you simply use them and see where they connect in the cortex. Here things get a little bit tougher because in a lot of cases nobody really knows where they should connect in the cortex. In some, like we looked at like the lateral geniculate nucleus, and it projects onto the visual cortex like you'd expect. That's not really, LGN's not really brainstem, but it's down there and shows up in the ICA. Anyway, so this is another cluster of them. So I think really interesting field of study down there. Now, what we think we really need to improve the encoding, you think encoding in MR is done by the gradients. Well, that's actually kind of wrong, because the RF channels actually do more encoding when you're doing a factor of 9, 12, 16 encoding. Say you're doing multi-slice, multi-band 8 with 2 in plane, that's a factor of 16. So for every gradient encode line, you're generating 16 with the RF coil. So the RF coil really does the encoding, but the shim is actually also key for the encoding, because if you have a better shim, you can tolerate a longer EPI readout. You can tolerate a longer echo spacing with less and get a decent distortion. So so far as you can improve the shim, you can improve your spatial encoding, and I think we can get that next step down in image resolution. So this was a shimming project that caught our eye. It's the work by the Yale group, where they did a matrix shim approach. They used 48 little shim coils. Each one is 100 turns of wire, and they arranged it on a cylinder, as people are wont to do in MRI, for reasons not clear to me. And it does great. It really does a great job of shimming out these problem spots in the head. The only problem with it is that there's no place to put the RF coil anymore. They left this little gap in the center for the RF. That's simply not enough. And so we thought, well, these little shim loops, they want to be as close to the body as possible, just like the RF loops. And they both need to be small and close to get high spatial frequency patterns. The RF coil so it can reconstruct highly accelerated images, and the shim coil so that it can cancel very local shimming problems. They both want the same things. Why not make them one and the same? Why not use the same conductor for the RF coil and for the shim loops? And so we simply modified a standard loop that we use and added the capability to pipe a couple amps of current around the loop. And of course, the DC currents and the RF currents are 8 orders of magnitude apart in frequency, it's really not a hard RF engineering problem to keep them apart. The surprising thing is that, remember, the Yale group used 100 turns, and here we only have 1 turn. So does that mean we need 100 amps of current? That would be too much. But no, it turns out that by getting rid of the cylinder and putting them on the head, we improve the efficiency enough that we can get by with just a couple amps of current in each loop, which is really benign. So here's some models Jason Stockman did of various loop arrays, and including the Yale one. And here's how they perform just in simulation. The answer is pretty well, and he did spherical harmonics just for reference because that's the other way people like to shim. And I'll just point out that this is now with slice optimized shimming, global shimming. I'll stick with slice optimized. You can really see that with 128 channels, you really knock out some of these shim problems. And 32 is equivalent roughly to 4th order spherical harmonics. And that's a complete set of 4th orders, not just 1 or 2. And the 128 is equivalent to roughly a full set of 6th order spherical harmonics, which is a completely unwieldy beast to try to make. So I really think that this is the way to get it done. So we decided to try to build one, a 32 channel coil. We added the DC stuff. Gets a little bit messy, I must admit, and but a lot of work. Then of course we need a shim amplifier. So we built some shim amplifiers. These are current feedback loops. They're linear devices. They cost about $100 a channel to build. They're digitally programmed. There's an ADC on board. They're water cooled. They generate a lot of heat, but they can be switched fast. In about 20 microseconds, we can switch on the current in one of these loops. That's what we need for slice by slice shimming. That's hard to do in spherical harmonics because of the big inductance. It's also a problem in spherical harmonics because you switch fast, you generate eddy currents in the bore. Well, in this case, this little loop is so far from the bore, eddy currents don't seem to be a problem. So it really solves a couple of issues. So here's our little boards and a big power supply, sits outside the room. The boards are non-magnetic, so they sit right behind the magnet. Here's the final coil. It tested out pretty good. It heats up a little bit, but less than 2 degrees when it's full current, and we call it the AC-DC coil. And we did lose a little SNR when we hooked up all this junk to our 32 channel coil. We had a before and after test, and the after is a little bit worse. But it's not horribly worse. This is a commercial coil, which is not quite as good because ours is shaped a little more tightly around the head. So we're going to try to fix that. We didn't make any attempt to go back and fix it. Here's the sort of field patterns you get when you put an amp through one of the windings, and they're exactly what you'd expect. Biot-Savart law works. And interestingly enough, with 32 channels, you can drive combinations, and you can drive linear shims or spherical harmonics as you like, because you have a lot of coils to put current through. And this might be maybe a Patlock, a lightweight Patlock coil. It doesn't produce very high fields, but you might think about trying to encode with some of these if you were interested in that sort of thing. Here's how it worked. Here's a magnitude image, the field map with just the second orders, the predicted field map using the field model that we had, and then the actual measured field map with the current going to the shim array. You can see it's a little disappointing. We didn't quite get the full predicted value, but I think we did pretty good. And the total shim current is quite reasonable, 10 amps integrated over all the devices. Echoplanar distortion. Here's some field maps, showing the acquired map and how it started after second order shimming. And you can see this effect in the EPI images. You can see it squashing down about 2 or 3 centimeters here. It's not doing that anymore. Matter of fact, it might have kind of overdone it at the edge. I think we might have to play with exactly how we do this optimization boundary. Anyway, that's it for the shimming. I want to finish up in 2 minutes. Wow, 2 minutes with a completely different idea for brain scanning technology. It was really inspired by this Berlin project of putting a CT scanner in an ambulance. The idea is to try to dispatch this ambulance to people who might have a stroke, take an image and look for a cerebral hemorrhage, which is of course a contraindication to the only known stroke medication, which is an antithrombolytic. So by taking the image like 30 minutes earlier, you might be able to save, several million brain cells. So we set out to try to build a portable brain scanner. Of course, if CT can do it, then MR should be able to do it better. But by portable, it's really tough, because I really want it so that I can pick up the magnet with one hand and the electronics with the other and carry it across the room. And that you have no special installation requirements, no power, no cryogens, no venting, no shielded room, no ferrous exclusion zone. So this is something Clarissa Zimmerman and Jason Stockman in my lab have been working on. It's also motivated by ultrasound. In ultrasound, you have expensive, full, high-end units, you have portable units, and you have really portable units that even Jack Welch can use. And the market seems to have no problem with this. In MR, we have 3 sizes: really big, very big, and big. And so why don't we have something smaller? And so I kind of compiled the top 10 reasons shrinking MR doesn't work. One is it's already been shrunk down. The manufacturers work really hard to try to make those things as small as possible, as short as possible. It's already been done. That's the main focus, actually, I think, of commercial MR engineering. So that's one answer. There's other reasons that homogeneous and strong magnets are just big. So you're going to have to cross out homogeneous, and you're going to have to cross out strong. Gradient coils must produce encoding fields large compared to the magnetic inhomogeneities. So you're going to have to, if you have an inhomogeneous magnet, you're going to have to cross out gradient coils. Low field magnets just have too low of an SNR. This is not really true. There's 0.2 Tesla magnets earning their keep in the clinic every day around the world. They take okay images. They're not as good as a 3T. But this one I would argue with. It's not really true. When you get below that, so 2T is fine. Here's a 0.35 diagnostic scan. Inhomogeneous magnets don't produce images. We'll have to fix that one. And everybody wants the best image possible. That's probably true, but it shouldn't be true. And that goes back to that case of ultrasound. That little handheld ultrasound doesn't take as nice a picture as the big expensive one. And somehow they use the right one for the right job, and they manage it in ultrasound. In MR, that seems to be beyond us. So we wanted to replace the B0 and gradient coil with a rotating permanent magnet. So we want to put the inhomogeneity of the magnet, the lightweight magnet, to work and use it as an encoding field as it rotates around. So there's less power because there's no gradient or magnet power supply. It's inhomogeneous. It lowers the magnet weight. We want something like a 1 to 2 millimeter target resolution with nice thick slices, 5 millimeter slices. No sound, no cryogens, no special sighting, no ferrous exclusion zone. With a couple inches of padding around the magnet, scissors and keys don't stick to it. The drop-off of these permanent magnets is so fast, they just don't stick. No RF cabin. We'll probably use a conductive cloth that we drape over the subject, and no water cooling. So you want to be able to sight this in your oncologist office, in your neurosurgeon's office. They're not going to put in 480 volts, 200 amp lines to do that. You simply have to get it down to normal power requirements. And our main target, one of the main ones, is bleeds. We talked about the hemorrhagic stroke, but also in subdural hematomas, intracranial hematomas, post-surgical bleeds. Tumor follow-up, just to look at the edema, even. Shunt malfunction and hydrocephalus checkup. They put in these shunts, and they need to make sure they don't clog. The ventricles are draining. This is something that is done by, you can see it in the scout image of a 1.5T. It's not a great image needed. You just need an image inside the brain. And suitable for locations in all over, emergency department, ICU, battlefield, ambulance, rural clinic, developing world. So here's our magnet, and here's the idea. The inhomogeneous fields The field of this Hallbach magnet is transverse, and it has a roughly quadratic sort of inhomogeneity pattern. We stick the head in, and then we rotate it around, taking spin echoes as we go to produce an image with variable resolution. Since the encoding field, the lines are spaced closest together near the edge, you're going to get the highest spatial resolution there. In the center, you actually get an encoding hole. For those of you not familiar with the Hallbach design, it works just like birdcage coils. If you're not familiar with birdcage coils, sorry. But we use the same mode, which we get a nice transverse uniform field just by rotating the phase of these magnets 0 to 2 pi around the loop. You can buy these magnets at gaussboys.com on the internet. They're sold basically for hobby purposes, but they will take your fingers off. Believe me, you want to be a little careful. It's a 45 kilogram magnet. This is the one we settled on. It's not quite big enough. You can just fit a head in, but it's not quite big enough. Transverse B0, here's a field model of it. It looks nice and uniform there, but it's about a 1% homogeneity. That's, of course, not enough for MR. It's about 1,000 times poorer than you do. Oh, and it's a 0.77 Tesla, so about 2 orders of magnitude below your 7 Tesla, 3.3 megahertz. There it is built. Here's the field pattern we mapped. So the idea is that you rotate this thing around, acquire these generalized projections onto the nonlinear field, and you have this multipolar spatial encoding. Here's 2 phantoms in this field. You see the different patterns. You can project where these reconstruct an image, but you'll get a ghost because there's a frequency ambiguity in the quadratic pattern. That's well known to the Patlock people. So we use the same trick and use array coils. And here's the thing of the thing working. I'll just cut right to the chase there. It's rotating around. Every rotation period, we take about 64 echoes. We have to know the field, of course, to reconstruct the image. Image is reconstructed with just a generalized encoding matrix. Just knowing the fields and the rotation angles and the different coils, you form one big matrix and then invert it or numerically solve it with a conjugate gradient type algorithm. And the first thing you learn is that these quadratic fields, of course, have this encoding hole in the middle. As you go to and add a linear term, it gets better. So this bottom one now has a linear shim coil, a linear shim term. So the encoding hole is here. It's actually not on the same axis as the axis of rotation. And that does a nice job of getting rid of the total loss of encoding in these center points. This is a little point spread function simulation. Of course, if you have a linear field, then the resolution is uniform. So here's some models showing how it should reconstruct a brain, showing the encoding hole. As you get more and more of a linear field, we think this one is acceptable. And then, of course, if you have a pure linear, it becomes quite nice. And here's some of our first images taken with a phantom carefully prepared to hide the encoding hole from our funding agency. But we just wanted to see if we could get an image, and it's actually quite good. It's something like, a millimeter resolution outside. Here's a lemon slice off axis. There's the encoding hole, so we still have to do something about that. These are rather long images, but we don't have parallel receive, so we have to repeat it, one for every receive channel, and that's a little tedious. So it would be 8 times faster if we had a real console. So our next step is to implement encoding in the third direction with RF encoding. There's several published ways to do that. We'll implement this linear shim to get rid of the encoding hole. And we've arranged to try a prototype at the MGH emergency department in Neuro ICU. And we've also arranged to build one for the Cure Uganda Children's Hospital in Uganda, which here's a picture of it, which if we succeed, we will be the first MR scanner in Uganda. And this hospital specializes in hydrocephalus stent or shunt placements. Here's how the shunt goes. And they really just need to see whether these ventricles return to normal sizes. So I think we can actually do that with a 2 millimeter, 3 millimeter resolution image. So I thank you for your attention. I've already gone over.